recording.
Thank you, madam.
All right. So maybe if about, I think we have 1 minute. If we can recap what we did last week, then we'll continue from there. Microphone. Is my microphone on or turned it off? The microphone is on. All right, so last week we started with matrices. We looked at what a matrix is. Also, we looked at some of the special matrices. We couldn't cover all of them. There are so many matrices, but we only covered a few that will be important in our field. Then from there, we looked at some of the operations that can be performed on matrices. We looked at the transpose, and based on the transpose, we're able to determine 3 types of symmetry that exist in a matrix, whether it is symmetric. Symmetric here means that A transpose is equal to A, all right, where the transpose is changing all our rows into columns and all our, or it's not and, or changing our columns into rows. And if A transpose is not equal to A, then it means that A is anti-symmetric matrix or asymmetric. Then we realized that there were some types of matrix that although A transpose is not equal to A, but A transpose is equal to negative A. And such matrices, since the symmetry only exists between A transpose and negative form of A, but not A transpose and A, we say that this is skew symmetric matrix. All right, so it's more like slanted. It's almost there, it's not there, halfway. Then we also looked at the second operation, not in the sense of in the order, but the second operation that we looked at was the addition, and then we also looked at the subtraction. And for the addition and subtraction to be possible, the matrices involved in this operation must have the same dimension. So if the first matrix is m by m, then for the first matrix to be added to or subtracted from the second matrix must also have the same dimension, n by m. If the dimensions are not the same, then addition and subtraction will not be possible. We also took a look at the 2 types of multiplication that exist, 2 known type of multiplication that exists in matrices, and the 2 are scalar multiplication and product of matrices. When it comes to scalar multiplication, we are only looking at a number, which is in the set of all real numbers, and a matrix, okay, which is in the set of all matrices of the dimension m by n. It does not necessarily need to be a square matrix. So to perform a scalar multiplication, we multiply the scalar by each and every component of the matrix. So assuming A is equal to 1, 2, 3, 4, then small a times matrix A is A times 1, that will be A times 2, that will be 2A, A times 3, that will be 3A, and A times 4, that will be 4A. And that is what scalar multiplication is. Then we also looked at the other type of multiplication, which is the product of matrices. And in this case, what we have is all matrices. Yeah, I'll be with you. So all we have is matrices multiplying each other. So for the product of 2 or more matrices, 2 matrices to be possible or to be defined here means that for the answer to exist, the number of columns in the first matrix must be equal to the number of rows in the second matrix. So last week we were able to deduce a quick way to check whether the product of two matrices is possible. And that is to write down the dimensions of the two matrices involved, making sure that the first dimension that you write corresponds to the dimension of your first matrix, followed by the dimension of your second matrix. So assuming that matrix A, the dimension of matrix A is m by n, and the dimension of matrix B is, say, x by y, then to know whether A times B is possible or not possible, we write down the dimensions of the two matrices, right? So we write down the dimension of the first matrix, which is m by n, followed by the dimension of the second matrix, which is x by y. Since the product is only defined if and only if the columns in the first matrix is the same as the rows in the second matrix, we look at which of these numbers represents the columns in the first matrix. The dimension of a matrix is given by the number of rows by the number of columns. So if you look at the dimension of any matrix, the second entry represents the columns. All right, so n represents the number of columns in matrix A. And the number of rows in matrix B is represented by x. So if these two inner numbers are the same, if n is equal to x, then A times B is possible. And if it's possible, then it means that the dimension of the resulting matrix is given by the numbers outside the inner numbers. So we'll have m by y matrix, all right? So given that the dimension of matrix A is 2 by 100, and the dimension of matrix B is 100 by 1, to determine if A times B is possible, we write down the dimensions of the two matrices, 2 by 100, against the dimension of the second matrix, 100 by 1. This first 100 here corresponds to the number of columns in the first matrix, and the second 100 here corresponds to the number of rows in the second matrix. And since columns in the first matrix is the same as rows in the second matrix, it means that A times B is possible. And if it's possible, then the dimension of the resulting matrix is 2 by 1. So you have to first of all check if what you're going to look for will exist or will not exist, because it's not all products of matrices that is defined or that is possible for you to find. Now, if we look at the same two matrices, A times B is possible, and the dimension of the resulting matrix is 2 by 1. Let's see if B times A is possible. B times A means that the dimension of our first matrix is 100 by 1, followed by the dimension of our second matrix, which is 2 by 1. For B times A to be possible, it means that columns in our first matrix must be the same as rows in our second matrix. But columns here is not the same as rows in our second matrix. Therefore, B times A is not possible, right? So we simply write undefined. So you notice that for the same two matrices, A times B exists, and the dimension is given by 2 by 1. But for B times A, this matrix does not exist. Okay, so since A times B is not the same as B times A, we say that multiplication of matrices is not commutative. If A times B is always equal to B times A, then we'll say that the multiplication of matrices is commutative, but that is not the case. So let's take a look at one or two examples and see how it's done. Given any two matrices, A, which is 2, 1, 3406. Matrix B, which is maybe negative 5, 2, 1. Then maybe the second column, let's say 3, 7, 8. First, we need to check whether A times B is possible and see if we commute them, the results will exist. So A times B, to determine whether it's possible, we first write down the dimension of the first matrix, which is 2 by 3. Write down the dimension of the second matrix, 3 by 2. All right, so since the two inner numbers are the same, it means that A times B is possible. And if it's possible, then the dimension of the resulting matrix is going to be 2 by 2. If we check for B times A, the dimension of B, 3 by 2, dimension of A, 2 by 3. The two inner numbers, once again, are the same. And so the dimension of the resulting matrix is going to be 3 by 3. All right, so this is another example why the product of matrices is not commutative. A times B is giving us a 2 by 2 matrix, and a B times A is giving us a 3 by 3 matrix. So let's take a look at A times B first. Then we'll also take a look at B times A. So we have 2, 3, 0, 1, 4, 6. Multiplying B, which is minus 5, 2, 1, 3, 7, 8. This is equal to, open a big bracket. So to multiply these two matrices, we pick the rows in the first matrix and then multiply it by the columns in the second matrix. So if we pick the first row, we place it on the first column of the second matrix. All right, if you do that, you realize that we'll have 2 being placed on minus 5, 3 will be placed on 2, and 0 will be placed on 1. These two numbers that correspond, you multiply them, and the answer, you sum it. All right, so 2 will go to the first component, which is minus 5. So we have 2 times minus 5. Then we'll have 3 going on to 2. So we have 3 times 2. And we have 0 going on to 1. So we have 0 times 1. These numbers, we sum them. Now there is a second column in the second matrix. So what we just did, we do the same thing over here. We place the first row on the second column in the second matrix. So if you do that, 2 goes to 3. So we have 2 times 3. We have 3 going on to 7. We have 3 times 7. And then we'll have 0 going on to 8. So we have 0 times 8. These numbers, we sum them. There are no other columns in the second matrix. Okay, so we close the bracket and then move on to the second row. Once again, the second row on each and every column in the second matrix. All right, so if you do that, 1 goes to minus 5. So 1 goes to minus 5. So we have 1 times minus 5. 4 goes to 2. So we have 4 times 2. And then 6 goes to 1. So we have 6 times 1. These numbers, you sum them. We move on to the second column. 1, 4, 6 placed on 3, 7, 1. Okay, so we have 1 times 3, 4 times 7, and then 6 times 8. These numbers, you sum them. Please, there is no operator between these two entries. There's no operator between these two entries. It's just space. Do not put addition or subtraction or any other number there. Okay, so the rest is just simplifying. We have 2 times minus 5, that will give us minus 10. 2 times 3, that will give us plus 6. 0 times 1, that will give us 0. Then we move on to the second column. We have 2 times 3, that is 6. plus 3 times 7, 21, plus 0 times 8, that is 0. We move on to the second row. We have 1 times minus 5, that is minus 5, plus 4 times 2, 8, plus 6 times 1, that is 6. And then the last entry, we have 3 plus 28 plus 48. And this will give us the working calculators. We have minus 4, 27, 9, and then 28 and 48 will give us 76. 76 plus this will give us 79, which is a 2 by 2 matrix. Now, if we are to switch it around and find B times A, we can see that the dimension of the resulting matrix that we should expect is a 3 by 3 matrix. So let me clean this side and so B times A, which means that our first matrix, which is B, given by minus 5, 2, 1, 3, 7, 8, is multiplying matrix A, 2, 1, 3, 4, 0, 6. All right, so to multiply these matrices, we pick the first row in the first matrix, place it on the first column, on the second column, and then as well as on the third column. All right, so this is equal to, if we place the first row on the first column, we'll have minus 5 matching onto 2, so minus 5 times 2, and then 3 matching onto 1, so we have 3 times 1. The results, we sum them. When we are moving on to the second column, you do not put addition over here. You just leave it blank, all right? Just space between the components. Then the same first row on the second column, we have minus 5 moving on to 3, and then 3 moving on to 4, and the results, sum them. We are moving on to the third column. So we have minus 5 moving on to 0, and then 3 moving on to 6. There are no other columns in the second matrix, so we can close our bracket. And then we move on to the second row in the first matrix. If we pick the second row in the first matrix, we place it on each and every column of this matrix. So we have 2, which is the first component in that row, going on to the 2 here, which is in the first position of the first column in the second matrix. So we have 2 times 2, and 7 goes to 1. So we have 7 times 1. The results, we sum them. We move on to the second column. 2 will go to 3. So we have 2 times 3. And 7 goes to 4. So we have 7 times 4. The results, we sum them. Then the last, we have 2 times 0. There's an additional filter here. Times 0. Then 7 times 6, and the result is sum them. We'll now come and pick the third row and then do what we just did with the first row and the second row. So here we'll have 1 times 2 and 8 times 1, and the results, we sum them. 1 times 3, 8 times 4, the results, we sum them. And 1 times 0, 8 times 6, the results, we sum them. Right, so if we simplify this, we have minus 10 plus 6, minus 15 plus 12, 0 plus 18, 4 plus 7, 6 plus 28. Yes. And then 0 plus 42, 2 plus 8, 3 plus 32, 0 plus 48. So this will give us minus 4, minus 3, 18, 11, 34, 42, 10, 35, 48, which is a 3 by 3 matrix, just like we're able to determine or deduce from that simple approach of determining whether the product of two matrices is possible or not possible. Okay, so that is where we got up to. And so today we'll be looking at inverse of matrices. And if after that we have more time, we'll be looking at the first application of matrices. And then we'll end the class. But I need to make a small announcement. The timetable, there is a conflict with the DITs. Last week they joined us because their English class was canceled. The lady was not feeling well. And so what we're going to do is we'll do 2 hours on Fridays. Okay, so I'll do 2 hours on Fridays with you and then do 2 hours on Friday with them. And on Thursdays from 8:30 to 9:30 is where we're gonna place our 1 hour, because I also have 1 hour with them from 8:30 to 9:30 on Thursdays. So on Thursdays, we'll all join over there from that one period for tutorials where all questions, something that you did not really understand, you want clarification, assignments, class exercises will be done. So from now on, it's gonna be 2 hours on Fridays. If there wasn't any English class, then we could all join and then do 4 hours on Friday instead of the splitting 2 hours here, 1 hour there. Okay, so today we're looking at inverse of matrices. Which will be the first operation, the last operation that is performed on matrices that we'll be looking at. We don't really need to look at the other operations, just these will be fine. All right, so given any matrix at all, if we want to determine whether the inverse of the matrix will exist or the inverse will not exist, first of all, the dimension of that matrix must be square in nature. That is, the number of rows must be the same as the number of columns for us to even consider whether that matrix is invertible or not invertible, where invertible is it an adjective or it's a verb? I think it's an adjective. It describes a matrix whose inverse exists. Okay, so if I can somersault it in terms of matrix, and somersaulting here does not mean like a physical somersault of somebody, but in terms of matrices, if I can find the inverse of it, then we'll say that such a matrix is invertible. So for us to even consider whether the inverse of the matrix will exist or will not exist, the matrix needs to be square in nature. So the number of rows must be equal to the number of columns. If we have a matrix of the form n by n, where n is not equal to m, then the inverse will not exist. Okay, so we only look at square matrices. All right, so given any square matrix, the inverse of such a square matrix is given by a to the power minus 1, and this is 1 over determinant of the matrix times what is known as the adjoint of the matrix. That is how we find the inverse of a matrix, given any square matrix at all. It doesn't matter whether it's a 2 by 2 matrix or it's a 3 by 3, 4 by 4, 1,000 by 1,000. If we want to find the inverse of the matrix, it's given by 1 over the determinant of the matrix times the adjoint of the matrix. The determinant is sometimes written as det of A, where the det represents the short form of determinant. In some books, it's given by the absolute value of A. Okay, so from this formula here, let me rewrite the formula. Given in the matrix A, all right, the inverse of this is given by 1 over the determinant times the adjoint of the matrix. Now, this means that if the determinant is equal to 0, okay, from this formula here, if the determinant is equal to 0, then we have A inverse is equal to 1 over 0 times the adjoint of A. 1 over 0 is undefined. So we have undefined times adjoint of A. The adjoint of A is another type of matrix that you deduce from A. All right, so assuming that the adjoint of A is given by randomly, okay, it's given by A, B, C, D, where A, B, C, D are all numbers, then this inverse is undefined times A, B, C, D. If this undefined, we assume for it to be a scalar, then this is known as scalar multiplications, where we multiply the scalar by each and every component of the matrix. So this is going to be undefined, 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 right? Which means that the whole matrix now becomes undefined. If you have a matrix which is undefined, then it means that matrix does not exist. Okay, so if the determinant is 0, it means that the inverse does not exist. And if determinant is equal to 0, the inverse does not exist. And if the inverse does not exist, then we say that the matrix A is non-invertible or singular. Because of the fact that if the determinant is 0, we're going to have 1 over the determinant, which is 0. 1 over 0 is undefined. That makes the whole thing undefined. All right, so if the inverse does not exist, then it means that we cannot find the inverse of A, right? It means that the matrix itself is non-invertible, where invertible means that the inverse exists. So if the inverse does not exist, then we say that it is non-invertible or singular. But if the determinant is a non-zero number, then the inverse is 1 over that non-zero number. Okay, let's call it alpha times the adjoint of A. Once again, let's assume that the adjoint of A is A, B, C, D. Okay, so this is 1 over alpha times A, B, C, D, where 1 over alpha will be a number, okay? Number multiplying a matrix, scalar multiplication. So we multiply that scalar by every component of the adjoint. So we have 1 over alpha times A, that will be A over alpha. We'll have B over alpha, C over alpha, and D over alpha. All right, so here the inverse exists. And if the inverse exists, then we say that the matrix A is invertible or non-singular. Okay, now let's look at how to find the inverse if it exists. How to find the inverse if it exists and if it does not exist. Have we lost anyone so far? No, okay, so we'll start with the simplest one, which is the simplest form of a square matrix, which is a 2 by 2 matrix. Okay, so given a 2 by 2 matrix A, whose components are A, B, C, D, then the inverse of A like we said earlier on, it does not matter that the dimension of the matrix. The inverse of A is always given by 1 over the determinant times the adjoint of the matrix. Now, to find the determinant and the adjoint of the matrix depends on the dimension of the matrices involved. The approach you use in finding the determinants of a 2 by 2 matrix is not the same as the approach you use in finding the determinant of a 3 by 3. And as you move along, it gets much more complicated. That is where we need to write codes to be able to help us go through. All right, so for a 2 by 2 matrix, the determinant of A is given by the product of members on the leading diagonal, AD, minus product of members on the other diagonal, BC. And the adjoint of the 2 by 2 matrix is simply swapping the positions of members on the leading diagonal. All right, on the leading diagonal, we have AD. And in the adjoint form, we swap these positions. So we have DA and negate the other component. So instead of B, we'll have minus B. And instead of C, we'll have minus C. All right, so it means that the inverse of A will be 1 over AD minus BC times the adjoint, which is D minus B minus C and A. Now let's use real numbers and see how this pans out. Given any matrix, square matrix, matrix B, let's say this is 2, 3, 4, 7. To find the inverse of this matrix, we need to find 2 entities. One, we need to find the determinant of matrix B, and we need to find the adjoint of matrix B. Now, in some cases, some people prefer to find the adjoint followed by finding the determinant, but it is much more convenient to find the determinant of the matrix first, because if the determinant is equal to 0, then you know that what you're even going to look for does not exist. So you wouldn't even worry yourself going through that tedious approach of finding what the adjoint is. Okay, so first of all, find the determinant first. If it's a non-zero number, then you know that the inverse will exist. So you go ahead and find the adjoint. But if the determinant, as soon as you find out that the determinant is equal to 0, then you know that the inverse does not exist. And so you don't worry yourself finding what the adjoint is. So given a matrix, matrix B, we first of all find the determinant of this matrix, which is given by the absolute value of B. And this is absolute value of B. So we have 2, 3, 4, 7. So if you see absolute value around a matrix, it means you're looking for the determinant. And if it's a square bracket or a round bracket, then it means it's a matrix or it's a vector. Okay, so this is equal to product of members on the leading diagonal, 2 times 7, minus product of members on the other diagonal, which is 3 times 4. All right, so if we simplify this, 2 times 7, that is 14, minus 3 times 4, that is 12. Right, so 14 minus 12, this is 2. This is a non-zero number, okay? And so it means that the inverse exists. Therefore, matrix B is vertible or non-singular. So we find the adjoint of B since the determinant is non-zero. And because it's a 2 by 2 matrix, we simply swap the positions of members on the leading diagonal. All right, so instead of the leading diagonal reading 2, 7, in the adjoint form, it reads 7, 2. Then the other components, we negate them, minus 3, minus 4. So now we know the 2 entities that are involved in the inverse of the matrix, which is the determinant and then the adjoint. All right, so the inverse of the matrix is equal to 1 of the determinants of the matrix times the adjoint of the matrix. And this is equal to 1 over the determinant, which is 2, times the adjoint, which is 7 minus 3 minus 4, 2. This is scalar multiplication. So you multiply the scalar by every component of the matrix. So we have 1/2 times 7, that is 7/2 minus 3/2, minus 4/2, that will be -2, and 2/2, that will be 1. So this is the inverse of matrix B, where B is 2, 3, 4, 7.